Starting with the last term question then, it says, what process would we need to use to separate two liquids with similar boiling points? Well, hopefully you've realised if we've got a mixture of two different liquids that we're going to use distillation. However, if they've got similar boiling points, then the type of distillation we need to use would be fractional distillation. If we look at the last month question, it says a student carried out chromatography experiment on 4 inks. Calculate the RF value for the spot in ink W. Well, I know to calculate RF, it's how far does the dot move divided by how far does the solvent move. Here, the spot in W moved 2 centimetres according to the ruler, and the solvent moved 6.5 centimetres. So the calculation I'm going to use is 2 divided by 6.5, and that gives me 0.31. Remember, the most common mistake here would be for students to do 6.5 divided by 2. But we know our RF value can never be higher than 1, because the furthest any of these dots can move is here with the solvent front. So if you get an answer of above 1, the likelihood is you flip the equation around, so try doing it the other way instead. Moving on to the last week question, you are asked to draw a dot and cross diagram for calcium chloride, CaCl2. Well, I know calcium is a metal because it's on the left of the periodic table, and I know chlorine is a non-metal because it's on the right of the periodic table. I know a metal and a non-metal forms an ionic bond. I also know calcium is in group 2, so it has 2 electrons in the outer shell, so it loses 2 electrons to form an ion with a +2 charge. Chlorine is in group 7, so it has 7 electrons in the outer shell, so it gains 1 electron to get a full outer shell, so chloride forms an ion with a -1 charge. The problem is, calcium is trying to lose 2 electrons, and chlorine only needs to gain 1. Therefore, I need 2 lots of the chloride ion. Each of them will take 1 electron from calcium, so calcium has now got a full shell with a 2+ charge, and the chloride has a full shell with a 1- charge, but we have 2 lots of the chloride in total to balance out that calcium. And don't forget, you only need to show the outer electrons for a dot and cross diagram. And then building on from last lesson, we looked at ionic formulae. So you're asked to figure out the formula of the following ionic compounds. Well, I know lithium is in group 1, so it forms an ion with a +1 charge. Fluorine is in group 7, so it forms an ion with a -1 charge. If you swap those numbers, I need 1 fluoride, I need 1 lithium, so therefore the formula would be LiF. Looking at sodium oxide, I know sodium's in group 1, so it forms a +1. Oxygen is in group 6, so it forms an ion with a charge of -2. If I swap them numbers, I need 1 oxygen and I'll need 2 sodiums. So my formula would be Na2O. And last but not least, we've got calcium chloride. Well, I know calcium is in group 2, so it forms a +2 ion. And chlorine is in group 7, so it forms a -1 ion. If I swap them numbers, I'll need 2 chloride ions, 1 calcium, to give a formula of CaCl2. In this lesson, we're going to be looking at ionic structures, so the structure and bonding formed by ionic compounds, as well as the properties of ionic compounds, including the melting and boiling points and the electrical conductivity. So, if you were to draw your dot and cross diagram for calcium chloride, we know it would look something like this. So you've got your calcium ion with a 2+ charge and your chloride ion with your -1 charge. We also know that opposites attract, and in our ionic bonding lesson, we defined what an ionic bond is, and we said it's the strong electrostatic force of attraction between oppositely charged ions. So you've got a positive charge, a negative charge, and we know those opposites will attract, and that attraction is what gives rise to an ionic bond. And we call that force of attraction electrostatic, and it's the name given to any attraction between opposite charges. So we will look at this later on when we look at metallic bonds as well. So it's the strong electrostatic force of attraction between oppositely charged ions. And I've put it in this yellow box because it's a key definition that you must learn for the exam. Because when you answer any question about an ionic compound, you have to refer back to this definition. So it's really, really important. And if you do learn it, it will make sure you can access the top marks and the top grades. Last lesson, I also introduced the idea that the ionic formula doesn't actually tell you the number of the atoms in the ionic compound, but more the ratio. So if we think about sodium chloride, we figured out that it was NaCl. But that does not mean that in an ionic compound there is one sodium and one chloride, because that's far too small for an ionic compound. In fact, all ionic compounds form what we call this giant ionic lattice. And that's what I mentioned about the formula telling us the ratio of ions instead, which meant that for every one sodium ion, there was one chloride ion. So for every positive ion, there was a negative ion surrounding it. And you can see that from the diagram of my giant ionic lattice. For every blue, so my positive ion, it's completely surrounded by a negative ion. And every negative ion is completely surrounded by a positive ion in every direction. So these are my giant ionic lattices. They do not form molecules because a molecule is a small group of atoms held together by bonds. This is not a small group of atoms. So ionic compounds never form molecules, and it's really key that you are clear on that distinction when we look at ionic compounds versus covalent compounds. These form my giant ionic lattice where there are alternating positive and negative ions. So every positive ion is surrounded by a negative ion, and every negative ion is completely surrounded by a positive ion. And these are held together by our strong electrostatic forces of attraction between the opposite charges, which holds it together. And you can see they pack really closely together because they're surrounded by opposite charges, which makes those attractions so strong and is going to determine the melting and boiling point of these compounds. So, thinking about our definition, do you think the melting and boiling point of ionic compounds is going to be high or low? So, ionic compounds will always have a high melting and boiling point. And that's because you're going to need lots of energy to break the strong electrostatic force of attraction between the oppositely charged ions. So as you can see, that is pretty much my definition from the yellow box. So that's why it's really key to learn that definition, because we're using it to explain the properties of these compounds. Ionic compounds have a high melting and boiling point because there are strong electrostatic forces of attraction between oppositely charged ions, so my positive ions and my negative ions, which require a lot of energy to break or overcome. So that is your textbook answer when you are asked to explain the melting and boiling point of ionic compounds. The other property you need to explain is whether they can conduct electricity. And what you need to realise is that in order to be able to conduct electricity, a substance needs to demonstrate two things. Number one, it must have charge. And number two, that charge must be able to move. So here, we're looking for a charged particle. Well, it's in the name. If it's an ionic compound, it must have ions. And if you think of our definition, we've got opposite charges, so therefore we clearly have charged particles, because we know an ion, which is every one of these are ions, is an atom with a charge. So yes, we have a charged particle. The second question is whether these ions can move. Well, in a solid, if we think back to our state of matter, we know the particles in a solid don't move. So that means that ions in a solid cannot move and carry a charge, So that means ionic compounds can never conduct electricity when solid because they can't move. And we say that ions are in a fixed position. So ionic compounds do not conduct electricity when solid because even though they have ions with a charge, those ions can't move. If you look at this giant ionic lattice, it's pretty clear that those ions would be unable to move. So in order to be able to conduct, we have to either melt the ionic lattice, so make it molten, or we have to dissolve it in water, and that means to make it aqueous. Only then will the ions be free to move. And again, your textbook answer will say, ionic compounds can conduct when molten, aka melted, or dissolved, as the ions are free to move and carry the charge, but they can't conduct when solid because these ions are in fixed positions. So they will only conduct when melted or dissolved. On this slide, it's just a little bit of contextual information, a little bit of application of chemistry from the Royal Society of Chemistry. So I want you to take a minute to read the slide and try and answer the 3 questions below. Looking at question 1, you were asked to give the chemical formula for common salt. So hopefully you know either from common knowledge or from chemistry that the formula of salt is sodium chloride, and that would be NaCl. You then asked to describe the typical physical properties of salt. Well, we know sodium chloride, sodium's a metal, chlorine's a non-metal, so salt is an ionic compound. So the physical properties, thinking of the last slide, is that it's got a high melting point, a high boiling point. It doesn't conduct when solid, but it does conduct when melted or aqueous, dissolved in water. And when you're asked to describe the structure and bonding, we know it forms a giant ionic lattice, which means it's held together by strong electrostatic forces of attraction between oppositely charged ions. So this last slide is just an example of an exam question showing the kind of language you need to use when answering questions. So it says, sodium chloride has a high melting point of 801 degrees. Explain why the melting point of sodium chloride is high. Pause the slides and have a go at answering this question. If we look at the mark scheme then, in your answer you must refer to strong forces of attraction between oppositely charged ions, which needs a lot of energy to overcome. And if you think about these first 2 points, this is our definition of ionic bonding. So you'll be able to score all the marks for this question if you just put in the definition, because it shows the examiner you know what the bond is that you need to break and therefore link it to energy. And it does say on the right hand side, if you mention the word molecules, you will not get the mark. And we said giant ionic lattices do not form molecules. So you will lose mark if you mention molecules.